Alô? Está? Começa? Está sim, okay? Good afternoon, everyone. We are really sorry for this delay. We were having some technical problems. And welcome to another seminar of our seminars of the IAG, the Astronomy Department. And today we are honored to have Dr. Phillip Galli with us. Many thanks, Phillip, for being here with us today, presenting your work. Let me just briefly introduce him. He got his bachelor degree in physics from the Instituto de Física da Universidade de São Paulo in 2007, and his PhD from here, IAG, in 2012. He was also a postdoc here, and afterward, he was a postdoc researcher at the Institute for Planetary Science and Astrophysics, and also at the Laboratory of Astrophysics from Bordeaux, both located in France. Currently, Phillip is a researcher at the Núcleo de Astrofísica da Universidade de Cidade de São Paulo, and his research is in the field of high-precision astrometry, low-mass star formation, young star clusters, and galaxy structure and dynamics. And today's presentation is entitled Dynamics and Evolution of Young Stellar Clusters. As always, please, the question will be asked after the presentation. If you have a question in the YouTube, you can write it down in the chat. So, well, Phillip,
okay, thank you.
We can start.
So, hello everyone. It's a pleasure to be here at IAG and to meet you all after so many years. So, my talk today is about the dynamics and evolution of young stellar clusters. So, this is a research field that is evolving very fast. And my plan for today is to give you an overview of what has been done in the last few years, and also how the research conducted by my team is helping to further develop this research area. So in this talk, I will focus on the study of young stars of a few million years up to about the age of the Pleiades. These objects can typically be found in star-forming regions, stellar associations of the solar neighborhood, and young open clusters. So nowadays, the study of young stars is an interdisciplinary research area, and in our team, we work in the interface between astrometry and astrophysics, using, for example, astrometric data and methods to solve open problems about star formation and galactic structure. Another important research branch of our team is radio astrometry, based on VLBI observations of young stars, which allows us to connect astrometry with radio astronomy. Our team is working not only with data published from large surveys of the sky, but it's also producing new data sets from follow-up observations and by reprocessing data from public archives. And of course, we have been using novel methods like machine learning techniques to get the best out of these data sets. So these are the main building blocks of my talk and the topics that I plan to cover today in my presentation. And all these subjects, they appear to be somehow unrelated at first sight, but there is one single information that connects them all and was responsible for making progress in the study of young stars, which is the distance of a star. So distances are very important in astronomy because we use distances to convert measurements that we get from observations into physical quantities. So for example, the angular dimension of an object in the sky into physical dimension, magnitudes into luminosities, and angular velocities into spatial velocities. And of course, this opens the possibility to investigate the spatial distribution of stars and clusters in the Milky Way, calculate the physical properties of stars like mass and age, and also to investigate the kinematics of stellar groups. Distance determination in astronomy has evolved significantly in the last 5 years. First, because of the new data that is available nowadays, in particular the parallaxes. And second, because of the new methods that are being used to calculate distances. Many recent studies are using Bayesian methods to convert the parallax into distance, Instead of the naive inversion of the parallax that was commonly used in the past, many people still use it, but this approach is only possible when there are no measurement errors in the parallaxes, which is almost never the case, even for the best parallaxes that we have nowadays. So the two main projects in astrometry that can deliver state-of-the-art data to calculate distances are the Gaia satellite and VLBI observations from the ground in the radio domain. The astrometric precision that we get from the two projects is about the same. It's in the micro-arcsecond level of precision. The main difference is that Gaia is an all-sky survey, and with VLBI observations we can only observe a few specific and remarkable targets with radio emission that can be detected by VLBI instruments. But what most people don't know is that the astrometric precision delivered by Gaia was not something new, because we had already achieved the same level of astrometric precision with VLBI observations before Gaia. What's great and fantastic about Gaia is that it's doing it for the whole sky. But one important point to keep in mind is that the Gaia satellite operates in the optical domain. So it is strongly affected by the high extinction that is often present in young stellar objects and star-forming regions. Another important point is that the Gaia satellite has a limited lifetime. So this means that it won't be collecting data forever. In this context, VLBI observations, they offer a promising alternative to overcome the problem about extinction and about extending the time base of astrometric observations. So in principle, the two projects, they complement each other, and there is no competition between them. So in the next few slides, I will summarize some of the main achievements in the field of young stars based on Gaia data. And of course, I won't have enough time to discuss everything. So for a more complete review on this subject, I suggest that you take a look at this book chapter published by our team for the Protostars and Planets meeting that was held in Japan 2 months ago. So after publication of the Gaia DR2 catalog, a number of studies, many of them based on machine learning techniques, led to the discovery of a significant number of clusters, associations, and co-moving stars. Hundreds of new open clusters of different age, density, and location have been discovered based on Gaia data, showing that the census of the clusters that we had in the Milky Way was far from complete before Gaia. So in this diagram, we have the new open clusters that have been discovered in black dots. But we have also seen the emergence of a new class of young and filamentary structures that are only now being identified with Gaia data. And in particular, we have seen the discovery of an extended stellar stream called Minegast-1 that covers more than 100 degrees in the sky, is located at only 100 parsecs from the Sun, and has about the same age of the Pleiades. We have also recognized a large number of stars as members of clusters that we already knew before Gaia, and also discovered many young local associations. For example, the Volands-Carina association and the Myrdal associations, which are now new components of the solar neighborhood. In this diagram, we have the Myrdal association, which has about 500 members and is located at only 150 parsecs of distance. But other studies have focused on searching for cluster members of clusters that we already know over extended regions. So this is because many clusters were poorly characterized in the past before Gaia, because the studies, the surveys were limited to small regions in the sky. So the basic idea behind searching for cluster members is that we take an initial list of candidate members that we know from other studies. So this is our prior knowledge about the cluster. We define a region of the Gaia catalog around the cluster, which will have typically a few millions of sources. And then we run a membership analysis and we get our cluster members. So the methodology that we use for the membership analysis was developed by our own team. You can find more details in the papers of Saro and Olivares. In this slide, I put only the main steps just to give you an idea of our methodology. So the first thing that we do is to define the representation space. So this is simply the space of parameters that we want to use to select the cluster members. Usually when we run this kind of analysis with the Gaia catalog, we use Pelpa motions and parallaxes as astrometric features, and then we take one color and one magnitude as photometric features. Then we take our initial list of candidate members, which will be used in the very first iteration of the method just to define the locus of the cluster in the space of astrometric features and photometric features. Then we need to model the field and cluster populations. So for the field population, we use Gaussian mixture models, or simply GMMs. And the cluster population is the result of two independent models, one for the astrometric space and another one for the photometric space. For the astrometric space, we also use GMMs, and for the photometric space, we use a principal curve that will define the empirical isochron of the cluster in the color magnitude diagram that we defined in our representation space. Okay? So the field model is computed only once, at the beginning of the membership analysis, and then it's held fixed. And the cluster model is updated in each iteration of the process. We compute Bayesian membership probabilities for all sources in the field and classify them as members and non-members depending on a probability threshold that is defined by the user. So this can be something like 50% or 90%, you decide. Usually when we run this kind of analysis, we run with different probability thresholds and compare our solutions. So the resulting list of cluster members that we get is used then as input for the next iteration, and this procedure is repeated until the list of cluster members remains fixed after many iterations. And finally, we define an optimum probability threshold based on simulations, and this is what we use to select the cluster members in our analysis. So we have applied this methodology to the coronal Australis star forming region over a very large field that was never investigated in the past. We started this study with an initial list of only 52 stars, which were the classical members of the region known before Gaia. All of them, they were very concentrated in the vicinity of the main molecular clouds. And after running our membership analysis, we end up with a sample of more than 300 stars, which are cluster members of this region. So this means that we have increased the number of members in this region by a factor of almost 5. But the most important result of our study was that we have discovered a new population of young stars with an age of about 10 million years that is more dispersed in the sky and located in the galactic north of the molecular clouds and has twice as much stars as the population located in the central portion of the complex. So the red points in this diagram illustrate the stars from the new population that we have discovered in this region. But Gaia data was also fundamental to improve and revise our understanding of some clusters that were a bit problematic in the past, like the Lupus region. So Lupus is located in a sky region between two subgroups of the Skull-Sun Association, so that membership in this region has always been a hotly debated topic. We applied our membership analysis using Gaia data and identified only 137 stars in this region. But the most surprising conclusion of our study was that about 80% of all classical members of this region that were identified before Gaia, they are now, based on Gaia data, more likely to be either background sources or members of the Skull-Sun Association. So based on this new sample of Lupus stars, we have, of course, revised the properties and structure of this region. We conclude, for example, that the Lupus clouds are all located at the same distance. They move with the same space motion, have similar age, which indicates that they all belong to the same region and have a common origin. So we have also applied the same strategy to the Chamaeleon star-forming region, following the same strategy, a new membership analysis, and then revising the properties of this region. But in this case, we derived a new distance estimate for the two subgroups in this region, which puts them about 20 and 30 parsecs farther away. So this has very important consequences to the physical properties of the stars that we derive based on distances. So in this panel, in this plot, we have on the left the HI diagram constructed using the distance that we had before Gaia. And on the right, we have the same HI diagram for the same sample of stars using the distance that we get from our study based on Gaia DR2 data. And if you compare the two panels carefully, you see that on the right, the stars are more shifted towards younger ages. So this means that the Chamaeleon region is younger than what we knew before Gaia. And based on isochrones, we estimate an age for the two subgroups of about 1 or 2 billion years, which means that they are really very young. So let me now change the topic a bit and start discussing other projects about young stars that go beyond the Gaia catalog. So the first project that I want to discuss is the Gold Belt Distances Survey. The acronym for that is GOBALANCE, and it implements VLBI astrometry for young stars. So the GOBALANCE project aims at measuring very precise parallaxes and proper motions of young stellar objects in 5 star-forming regions, namely Ophiuchus, Orion, Taurus, Serpens, and Perseus. For that, we use the Very Long Baseline Array, or VLBA, that is basically an array of 10 radio telescopes spread over the entire United States. And the longest baseline in this array goes from Virgin Islands to Mauna Kea, and it has about 8,000 kilometers. So when we have all the 10 radio telescopes scheduled for our observations, we can achieve a typical astrometric precision in the parallaxes of a few tenths of micro-arcsecond, which is about the same level of precision that we get from the Gaia satellite. We have been awarded more than 2,000 hours with the VLBA for the GOBALANCE project between 2012 and 2018. So this is our team for the GOBALANCE project. We had Laurent Lanard as the PI of the collaboration. Then we had a number of students and postdocs, including myself. I was working at IAG at that moment. And each one of us was responsible for a very specific task in this collaboration. In my case, it was the analysis of the data from the Taurus region. So I was responsible for the data reduction and scientific analysis. And we also had in our team a number of experts from different fields of astronomy, like radio astronomy, astrometry, and star formation that helped us in the analysis. So this is an extension map of the Taurus region with all the sources that we have observed for the GOBALANCE project in Taurus. We started this analysis with an initial sample of 86 sources, but we detected only 52 of them with the VLBA. And we verified that the 23 sources are more likely to be background sources because they don't move in the sky, and the remaining ones are indeed young stellar objects. But finally, we derive parallaxes and proper motions for only 18 of these sources, namely those that had enough data for the astrometry fitting. So about astrometry fitting, we need to distinguish between two cases. So the first one is when you have a single star. This is the easiest case. You just need to solve this system of two equations, and then you get the 5 parameters astrometric solution, including position in 2D, proper motion in 2 components, and the parallax itself. The second case is when you have a binary system, and in this case you have to distinguish between 2 situations. So the first one is when only one component of the system is detected. So in this case, what you get is a 12-parameter solution, including the 5 astrometric parameters plus 7 elements that describe the orbit of the system. The second situation is when we detect all components of this system. So in this case, we can fit one additional parameter, which is the mass ratio of the components. And by combining this information with Kepler's third law, you get the mass of the two components of this binary system. So let me illustrate our results for one star in Taurus, namely V1023 tau. This is actually a binary system, and we detected the secondary component in 2 epochs of our observing campaign. So in this diagram, you can see in blue the fit for the primary component, and in red the fit for the secondary component of the system. One particular thing about this system is that we have combined the observations from the Gobelins project with past observations that were available in the archives, and we have achieved a time base of 13 years of VLBI data for this system. This is much more than what we can get nowadays from the Gaia satellite, which is based on only 34 months of observation so far. As a consequence, we have derived proper motions and parallaxes that are more precise by a factor of at least 3 as compared to the latest version of the Gaia catalog. And of course, given that we have detected the 2 components of the system, it was also possible to measure the mass of the 2 components with a good precision. So by the time that we were writing the paper, the Gaia DR1 catalog was already public, and we decided to combine the 2 data sets to start a preliminary investigation about the structure of the Taurus region. And we found strong evidences that of distance variation along the line of sight, meaning that the molecular clouds of the Taurus region were not located at the same distance. This is what is illustrated in this diagram. And this was already enough to claim that the canonical distance of 140 parsecs that was commonly used in the past for this region was not representative of all portions of the complex. But we didn't put much emphasis on this conclusion, because at that moment we had a very small sample of only 30 stars, and we see that the Gaia parallaxes, they have very large uncertainties, and they were affected by systematic errors. So a few weeks later, after publishing our paper, the Gaia DR2 catalog became available, and then we combined the 2 data sets and started a second paper on the structure of the Taurus region, using a sample of about 300 sources, which is much more representative of the Taurus population than what we had before. So the most important conclusion of our second paper about the Taurus region is that it is composed of multiple stellar populations. Of course, this is something that other groups also found, but they used different methods, and because of that they got different number of subgroups. So for example, Luma in 2018 identified 4 subgroups based on a manual selection of the stars with common proper motion and parallaxes. Rocatagliata in 2020 identified 6 groups based on GMMs. And in our case, we applied a hierarchical clustering method called HMAC that was first applied in astronomy. So, and with this method, we identified 21 subgroups. So this is the solution that we get from HMAC. So this is our hierarchical tree. At the lowest level of the tree, we have the 21 subgroups that we discuss in our paper. So despite the very different number of subgroups that we found, we claim that our solution is fully consistent with the one given by Luhmann, with only 4 subgroups, because at the highest level of the hierarchical tree, our 21 subgroups, they merge and they form the 4 populations recovered by Luhmann. And what we see is that these 21 subgroups from HMAC, they are mapping the distribution of the molecular clouds in the Taurus region. And of course, one important conclusion of this was that the subgroups and the molecular clouds are located at different distances, with distances ranging from about 130 parsecs to about 200 parsecs. What's interesting to see is that some structures like this one, which links 1495, which is the main molecular cloud of this region, it appears to be connected with another structure in the plane of the sky, with this kind of filament in the plane of the sky. But after our study, we see that they are actually separated by 30 parsecs in distance, so they are not one single structure. So, another important conclusion of our study is that the molecular clouds in Lupus, they are not only located at different distances, but they also have different velocities. And we have also important internal motions in this complex. So the median intercloud distance in Taurus is about 25 parsecs. Now, if we assume that all of these subgroups formed together in the past and evolved from one single point, we need a crossing time of many million years to explain the present-day location of all stars in the way that we see them today. So, for example, if we take two subgroups of Taurus, Linz 1495 and Linz 1544, they are separated by 51 parsecs. They move with a relative motion of 2.4 km per second. So if we assume that they form together from the same point in space, we need a crossing time of about 21 million years to explain their present-day location. And this is much larger than the typical age of the stars in this region. So our analysis in Taurus suggests that the Taurus region is the result of multiple in situ star formation episodes spread over different locations of the complex that happened at the same time. Another important thing about the Taurus region is that, well, it is a star-forming region, so it has not only stars but also molecular gas. And in this plot, we have the velocity field of the CO molecular gas in this region that was obtained from the survey conducted by Goldsmith in 2008 from the 5 College Radio Astronomy Observatory Telescope. And we see a wide range of velocities for the CO molecular gas in this region, depending a lot on the portion of the complex that we look. So we decided to compare the cinematics of the stars with the cinematics of the CO molecular gas. And for that, we measure the velocity of the CO molecular gas at the position of each star in our sample. And then we compare the velocity of the gas with the radial velocity of the stars in our sample. And we found a very good agreement with a mean difference in velocity that is very close to 0 and a very low RMS of only 0.6 km per second. These numbers are much better than the ones that we had in the past, before Gaia, which comes, of course, from the more precise data that is available nowadays. So what we see from the Taurus region is that the two components of this region, namely the stars and the gas, they are very well connected and they share the same cinematic properties. So another project that I would like to discuss is the Cosmic Dance project that is complementing the Gaia catalog at the very faint end of the initial mass function by detecting the least massive members of a cluster that cannot be observed by the Gaia satellite. The PI of this project is VLBI from University of Bordeaux. So the acronym stands for Dynamical Analysis of Nearby Clusters. And well, the project aims at investigating the initial mass function of young stellar clusters based on a clean and complete sample of cluster members. The strategy that we use is based on 3 steps. So first, we produce catalogs of very precise proper motions and multiband photometry in the optical and infrared from observations collected by ourselves, but also from archives. And of course, for the clusters that we want to investigate. And these catalogs, they go much deeper than the Gaia catalog for the same sky region. And because of that, they are excellent data sets to search for faint sources. Then, of course, we need to run a membership analysis, and the methodology that we use is the same that I explained before. And finally, we perform spectroscopic follow-up observations of a few specific targets of particular interest. So in this slide, I will illustrate some results of the Cosmic Dance project for the Upper Scorpius Young Stellar Association. So in this case, we combined the Gaia and the Dance catalogs to perform a new membership analysis of this region and we identified 3,455 members, and 20% of them are new members of this region. But the most important contribution of our study was actually in the planetary mass domain, where the proportion of new members increases to about 75%. In particular, we have discovered a population between 70 and 170 free-floating planets. So the two numbers, they depend actually on the age of the association that we use to estimate the stellar masses. Given that the age of Hyperscorpius is not precisely known, we took two age limits of 3 and 10 million years. So the red isochron in this plot is the age for 3 million years, and the blue is for 10 million years. As far as we know, this is the largest and most homogeneous sample of free-floating planets that was ever discovered in a star-forming region. And of course, the discovery of such a large number of substellar objects is important for the initial mass function of the cluster, because as we can see in this plot, at the faint end of the IMF, we have to rely on stellar models that are not really good and demand further improvement. The discovery of such a large number of free-floating planets is of course in excess, according to the predictions of the core collapse prediction model, which means that other formation mechanisms for these objects must be at work at the same time. So one possibility that we discuss in the paper is that many of these free-floating planets could have been formed by the dynamic rejection in protoplanetary disks. So the success of this analysis in Hyperscorpius led us to idea to extend the analysis to other star-forming regions. In particular, I am leading the analysis of the Coronal Australis region again, but in this time using such a catalog of the cosmic density object. In these panels, we have some preliminary results which indicate that with the cosmic density catalog, we can indeed identify many more substellar objects in this region that could not be discovered in our first study based on Gaia data. Another project that we are conducting is about age determination. So the Kronos project aims at constructing a consistent age scale for the young stellar clusters in the solar neighborhood. The PI of this project is David Barrado in Spain. And the Kronos project aims to derive ages with 3 different methods, using data from high-resolution spectroscopy from our own observations and also archival spectra. So we are basically using 3 methods to estimate ages: the traceback analysis, the lithium depletion boundary method, and isochrones. In my case, I am particularly involved in the first part, which is the traceback analysis, that provides a dynamical age of the association. So in this method, we trace the 3D stellar positions back in time using the 3D spatial velocity of the stars, and we try to define the moment back in the past when the group defined its minimum size or minimum volume in space. And the time interval elapsed between that moment of minimum size and the present time defines the dynamical age of the association. So the traceback analysis is important not only to determine the age of the association, but also because it gives us the birthplace of the association. Okay? And one important advantage of this methodology is that it is completely independent of physical assumptions and stellar models. This is not the case, for example, of ages derived from isochrones that depend on our choice of the stellar models. So the first target for this project was the Beta Pictoris association in the solar neighborhood. And the main difficulty, the main limitation to our first study was the scarcity of radar velocity data and also the poor quality of the radar velocities that were available, particularly from the Gaia catalog. So to overcome this problem, we searched for public spectra in many archives and also started an observing campaign with different ground-based facilities to collect more data. In the end, we have developed our own methodology to process the spectra and compute radio velocities, and we applied this methodology to all spectra that we could find, not only the ones that we observed ourselves. And this, in the end, turned out to be very important because it gave us a more homogeneous sample of radio velocity measurements and also more precise data. Finally, we got a dynamical age of 18.5 million years for the Beta Pictoris association, which was the first dynamical age estimate for this group that was consistent with the age given by other methods. Another critical point in the traceback analysis is the metric that we use to define the size of the association. And this is important because we use the minimum size of the association to get the dynamical age. So in this plot, we have, in this slide, I will illustrate this discussion based on our results for the Tucana association that were published a few months ago. So in this plot, we have the size of the Tucana association as a function of time. Okay? Well, one very common approach is to use the standard deviation of the stellar positions as a proxy of the size of the association. But as we can see in this plot, this depends a lot on the direction that you choose. So this is not a good estimator for the size of the association. Another possibility would be to use the determinant of the covariance matrix, which is somehow related to the volume of the association. But for some clusters, as this one, we see that the curve has a kind of a plateau. This means that the age will not be well defined. Finally, one last possibility is to use the trace of the covariance matrix, which returns the sum of the variance in all directions. And this is what we used for Tucana and also for the Beta Pictoris association. Using this metric, we get an age of 38.5 million years, which was also the first dynamical age estimate for a cluster of this age of about 40 million years that was consistent with the age given by the lithium depletion boundary method. So another application of the traceback methodology is to investigate the dynamical evolution of the cluster in time and also the local history of star formation. In a recent study of our team, we investigated the Chi-4 open cluster that is also known as Alessi 13. So this is the closest open cluster to the Sun with an age between 30 and 40 million years. We performed a new membership analysis, investigated the age and kinematic properties of this cluster, and confirmed that it has very similar properties to the Tucana, Columba, and Carina young stellar associations of the solar neighborhood, which are all located in the same sky region. So we decided to perform a traceback analysis of the 4 subgroups of the 4 clusters, but in this case we used the mean position of the group and the mean space motion of the group in the traceback analysis. And what we found is that the Chi-4 open cluster was much closer to the Carina association in the past, with a separation of only 7 parsecs. So if we go back, you see that 7 parsecs is about the size of a young stellar association at birth time. So 7 parsecs is really very, very close. So the common age, the common cinematics and sky location of all these young stellar groups is hardly a coincidence, and supports the idea that they are somehow related and that they could be the remnant of a much larger system that formed together back in the past. So before finishing this talk, I would like to say a few words about the DISC project. The acronym stands for Dynamics and Evolution of Young Stellar Clusters. So the DISC project combines almost everything that I presented in this talk. And actually many of the studies that I cited, they were already conducted as in the context of the DISC project. So this project is led by myself and it's funded by FAPESP as in the form of an Auxílio Jovem Pesquisador. So for more than a century, our picture of the solar neighborhood has been based on the gold belt model. So this is basically a ring of stars and gas and dust. And what recent studies show is that the good belt is actually not a physical structure, but only a projection effect in the sky. So in this paper led by João Alves, they claim that many of the star-forming regions of the gold belt, they are now part of a large-scale structure in the form of a wave that extends by more than 2 kiloparsecs in distance, and it's called the Radcliffe wave. So the discovery of the Radcliffe wave raises new questions about how stars form and move, and whether star formation can propagate along this wave-like structure. It also opens for the first time the possibility that many of these young stellar clusters, which were believed to be isolated, they can somehow be connected with each other at a galactic scale. But nowadays we know that the Radcliffe wave is not the only large-scale structure of the solar neighborhood. Many of the well-known star-forming regions that I cited in my presentation, like Coirón Australis, Lupus, and Camaillion, they belong to a different large-scale structure that is called the split. So in this context, the DISC project aims to characterize these large-scale structures by investigating the young stellar clusters that belong to each one of these structures individually, in terms of the stellar population, cinematics, structure, age, and local history of star formation, using data from large surveys of the sky and machine learning methods. And then we plan to combine all these properties at a galactic scale to construct a 7D picture of our solar neighborhood based on 3D positions, 3D velocities, and age. Another important branch of this project is the search for substellar companions in long orbits around young stars with VLBI astrometry. So in this case, we plan to combine the observations collected for the Gobelins project with new observations that we are collecting right now for the same targets to get a time base of a minimum of 10 years of VLBI observations, which will be necessary to investigate to search for substellar companions in long orbits. So this is a very specific niche that cannot be explored with Gaia data alone, and our team is nowadays in a good position to lead this initiative. So this collaboration is an interdisciplinary research action because we have experts from different fields of astronomy collaborating with us, from astrometry, star formation, radio astronomy, statistics, and machine learning. We also have 2 students working on the project. We have Sabrina Silva, which is my PhD student. She's working on the young stellar clusters of the Radcliffe wave. We have Jéssica Gamboa as Iniciação Científica. She's working on the young stellar associations of the solar neighborhood that have been discovered with Gaia data. And we also have other fellowships for students that would like to join our project. So we have a webpage for the project, so you can find more details and updates and news in this webpage. We also have an astronomy blog that is devoted for outreach. And of course, we are open to any kind of collaboration for those of you who are interested in joining and collaborating with us. So I think that I will stop here, and I leave you with my 2 take-home messages. And I'm happy to take your questions now. And I thank you very much for your attention today.
Thank you, Philip, for this great talk. So let's move to the questions.
Hi, Philip. Very interesting talk. I wonder if you detect in some of the clusters you have been observing supernova remnants, for example, because they might be useful to date the clusters, since this is one of your objectives. And if not, why? Because we would expect that massive galaxies should be turned into supernova by now, no?
Well, thank you for the question, but well, in our case, we have been working mostly on low mass star forming regions, so we have only a handful of high mass stars. About supernovae, so What we had in the past was an idea that, for example, the gold belt was formed by the expansion of a shell that was caused by the explosion of a supernova that was close to the Cassiopeia-Taurus association. But this is something that has never been confirmed in the past, because, I mean, there are some evidences that could not be confirmed with this model. So I'm not sure whether there was really a supernova or not in this region. So I cannot say, I mean, and I cannot claim that we have something related to supernova in our clusters.
Okay, thank you.
We have a question in the Google Meet. Pedro, you can ask.
I think very nice talk. It's very nice to see the use of VLBI through the astrometry project, so it's very nice to learn. So I read a question. I won't say that you are the only one, there is anyone I know in Brazil that is asking for VLBI time quite often. So perhaps I'm missing someone, but I know that you are every cycle, almost every cycle, asking for VLBI time. So I need to ask if an improvement of the VLBI sensitivity, an improvement in the sensitivity would help to make this approach of astrometric calculation more easily or more popular in general, to include more faint objects. Do you have any thoughts about that? So thank you. So you think that you can, in the VLBI, that you have a very increased sensitivity would be very helpful for your project anyway. Thank you. Thank you for that.
The targets for a long time. Do you have, I guess you have good observations about the acceleration also, right?
Yes. Yes.
So is it enough to apply, I think Rama explained this about this method of perspective acceleration to infer distance to the stars with this data?
Well,
is it possible?
Talking about acceleration, this is something that we measured in our VLBI observations. So in many cases you have, for example, a binary system, but you cover only a small fraction of the orbit, so you cannot fit the full orbit. But when you try to fit it, assuming that it is a single star, although you know that it's not a single star, it's a binary with a small coverage of the orbit, sometimes it doesn't work. And if you add, let me go back to the equations. So one possibility in these situations is that we can add one more term to these equations, which is namely the acceleration. And then usually you get a good fit. But on the other hand, when you have this kind of fits, this indicates that there is something more in the system. So usually when we do this is when you have a binary system and you have detected only one component. And to try to fit in the classical form, you see that the residuals are not good. You add one more term, you get a better fit, but then this is something that you have to pay attention for, because it might be a component that has not been detected in your observations. So in the disk project, we are now trying to search for substellar companions around the stars. And one thing that we use is indicative to select our targets, because you cannot point the telescope to every target that you want to observe. So you have to select your targets for the proposal. It's exactly by looking at those that have acceleration terms in the solution, because this may be indicative of something else.
Right. So maybe for them it's possible to apply this technique of perspective acceleration to infer distance. Radial velocity, not the distance.
In this case, when you fit, including the acceleration, you already get the parallax, and then you get the distance from the fit itself. Okay. So I think that this is what you're saying, something else. Okay. It's not related to the astrometry fitting itself. Right. Okay. Right.
I have another question.
Yeah,
it's
sure.
related, if someone doesn't have it, about this analysis, this dynamical traceback analysis. I think you showed in slide 33. So it's necessary also to get the acceleration of the members of the group to make this kind of analysis, because I guess you have to reconstruct the potential to trace back to integrate back in time.
Exactly,
the position.
Exactly. So in this case, what you're doing is that you are integrating the orbits back in the past. Okay? So for that, you need to use a galactic potential. Okay? So this is something that we have incorporated in our analysis, the galactic potential.
Right, but the potential between the members, is it important for this?
I guess not. What we take is the potential of the galaxy, okay, not the interactions between the... I mean, this is something that, of course, we could try to do, but this is very, very difficult to quantify in practice, you know?
Thank you.
Okay, we have a question from Betch in the Google Meet.
Hi, Phillip. Very interesting talk, thanks. And I should confess that I entered late in your talk. But I have a question regarding star formation.
Yes.
Rates. When analyzing, galaxies with some activity, star-forming galaxies, starburst galaxies, ultraluminal infrared galaxies, liners, any sort of galaxies that still have some star formation evolution, we have to rely on the Kinematic law to infer the star formation rate and the dependence with the density of the system, right? But with these very precise, highly precise measurements that you guys are doing, you get some clues on, more precise measurements of the star formation rate. So do you have any clues on this, for instance, if we can rely on Kinematic law, because we know in practice that the star formation rate can vary in these systems in star forming galaxies in general, from galaxies with some activity of star formation. These star formation rates can vary between 1 and thousands of solar mass per year, right, for the star formation rate. So what do you have any clues on this, on how Kinematic law is reliable if we consider these local measurements more precisely?
Okay, thank you for the question, but actually I don't know how to answer, because actually we have not been working on this so far. So we have been working basically with the initial mass function of not the entire galaxy, but for specific clusters. And what we have been seeing is that many of the models that predict the counting of stars at a given interval of mass, specifically at the faint end of the IMF, they are failing. So we have been finding more members than what is predicted. But we have not been looking at these things at a large scale, as you ask, only at specific clusters.
Right, but even locally, do you have any clues towards, because we have the star formation rate for the galaxy, right? For our galaxy, our Milky Way. So these local measurements, do they indicate that the average star formation rate is fine, should be corrected?
I don't know. Honestly, I don't know. I prefer not to say anything because I'm not sure. I'm sorry.
Right. I'm asking this because, you know, for instance, for studying, let's say, starburst galaxies and understanding the evolution of these systems in the nuclear region, we do need precise measurements of the star formation rate. Mm-hmm. And of course, to rely on information in our own galaxy, but the nuclear regions of these starburst galaxies are actually proxies. I mean, we can model them with the initial conditions from the our local star-forming regions and the stellar clusters. That's why, in molecular clouds and stellar clusters. That's why I'm asking you about these measurements, how they fit or how they compare with the global estimates that we do to the Milky Way. But yeah, it's something that at least it's nice to see that we can get this more precisely, right?
Yeah, I think that this is a great idea. I will talk to my team because so far I have been working mostly with the shape of the IMF. And of course, we did it only for a few clusters. So even if I had a number about star formation rates based on 2 clusters, I think that this is, not precise enough to claim that this applies to the whole galaxy or to large-scale structures.
But at least it may have a trend.
Yes, sure, of course, yeah.
Okay. Thanks a lot, Phillip.
Okay, thank you.
Okay. Any more questions here? No? Oh, I have a small question. I am curious about how you show when you are estimating the minimum size of the cluster here. Is this an independent method that you use for determining the size? Can you explain a little how you compute this?
So in this plot, we have the size of the association as a function of time. So we trace the stars back in time, mm-hmm. and we compute the minimum size. Okay, but the minimum size depends on the metric that you use. Okay, many people like to use standard deviations and this kind of things as a proxy for size. But as we show in this plot, this is not. This depends on the direction that you look. Okay. So what we have been doing is testing different metrics to infer the size of the association. So one possibility would be to use the determinant of the covariance matrix. Because why? The covariance matrix is somehow related to how the stars are dispersed. Okay? To the dispersion of the data points in the sample. If you take the determinant, this is somehow related to the volume of mm-hmm. the sample, so the volume of the association. In principle, this is a good procedure, this is a good idea. But as I show in this case, it doesn't work because of this plateau, So even if you get a minimum here that is very close to the minimum that you get with other methods, mm-hmm. the uncertainty that you get with this curve is huge. It's 10, 20 million years. So in the end, the h that you get is useless. Okay. So then we tried a different approach, which is this one in yellow, which is the trace of the covariance matrix, mm-hmm. which basically means that we are taking the standard deviation of the stellar positions in each direction and combining them all.
Okay, I see.
So this is a better measurement for the dispersion of the stars, which give us an idea about the size of the association.
Okay. Oh, see. Yeah, it's much more clear now because
Okay.
I understood something completely different. Thank you.
Okay.
Thank you very much for this clarification. So if there is, we will thank again the speaker. Thank you so much. And we will ask everyone to join us for the coffee break here. And thank you. And we will cut the transmission. Thank you.